Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in Chapter 2, part of this playlist that I'm calling Discrete Random Variables. And let's jump to today's topic, which is Discrete Uniform Distribution. Suppose that the value of a random variable, x, is equally likely to be any one of k integers, 1, 2, through k, then the density function of x is given by this. F of x is equal to 1 over k for x in, the integers 1, 2 through k and 0 otherwise. Theorem, let x be the discrete uniform random variable with parameter k. The mean value of x is given by 1 plus k over 2. And now let's prove that. So the expected value of x, by definition, is the value it can assume times the probability of assuming that value summed over all possible values. Well, the density is 1 over k, which is not indexed, so I take it out front, and then we're just summing the integers from 1 to k, which is k times k plus 1 over 2, and then this reduces to the desired result. Next theorem, let x be a discrete uniform random variable with parameter k. The second moment of x is given by this, k plus 1 times 2k plus 1 over 6. And let's prove it. The expected value of x squared, or the second moment of x, is you take that value times the density summed over all possible values. And then when we plug in the density of 1 over k, it's not indexed, so it can come out front. And then this is just the sum of the first k integers squared. The sum of the squared integers from 1 to k. And that's a pretty famous formula. K times k plus 1 times 2k plus 1, which is 6, divided by 6. K's cancel, and the result follows. Now let x be a discrete uniform random variable with parameter k. The variance of x is given by k squared minus 1 over 12. And a quick proof of that is the variance of x, or the second central moment of x, is the expected value of x squared minus the mean squared. And we plug in the values that we achieved, in the previous theorems, simplify, and then the result follows. I'm not going to go into detail of that. Now, let x be a discrete uniform random variable with parameter k. The moment generating function of x is given by this. So it's the moment generating function of x. Oh, I wish I'd have put one more step in there. This right here, the expected value of e to the tx. And then that is just you take e to the tx times the density, which is 1 over k, and we get this. And actually, this piece right here is the moment generating function. It exists for all t and all x, and this is it. So we can take derivatives of this to create moments of x, and this is it. Some people like to go one step farther, and since this is reminds them of a geometric series from 1 to k, it simplifies to this. So see the k here, and then many treat this as the moment generating function. But when you plug in t equals 0, you get an error. You get 1 minus 1, which is 0, and you can't divide by 0. So this moment generating function is actually not very useful. It's convenient, it's tight, it's not a summation like this. But when you create this formula, you assume that this value here is not 1, which means t equals 0. And if it is, you're summing 1 k times, divided by k, you get 1. So some will treat this as the moment generating function, but it's not. It's this. So the proof is simple. The moment generating function is the expected value of e to the tx, which is this sum, right? Because the 1 over k is the density, and this is it. But then, of course, some people use the geometric series and create this formula. Let x be a discrete uniform random variable with parameter k. The cumulative distribution function of x is given by capital F of x is equal to x over k. Let's prove it. So f of x, the cumulative distribution function, is the probability that x is less than or equal to x, which means you sum the density from 1 to x, right? Because that's what we're doing. And when you sum a constant that many times, you just add it up that many times, but you're adding it up x times, so you get x over k, and then that's the cumulative distribution function. And I probably should put x, yeah, in this sum, x can't be less than 1. If it is, then it's 0. There needs to be some sort of condition there for that. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.